Cool. So hello everyone. My name is Wenjin Li. Today I'd like to present our novel approach on computer-aided design model search and retrieval using frequency domain file conversion. The work is supported by National Science Foundation, and the team includes Karri, Professor Gupta, Professor Nektarios, Professor Karri, and myself. So first, quick overview of what I'm going to present today. I will walk through the motivation behind why we need CAD search and what we did, and most importantly, to present our approach in details and run a quick demo. At the end, we will go over things like what we can improve in the next stage. So there are many motivations why we need to have the ability to search CAD files. Here we list a couple example reasons. So in today's world, digital CAD modules are widely used in the manufacturing industry, especially in additive manufacturing, which is known as 3D printing. And 3D printing covers a lot of different fields, such as robotics, architecture, fashion design, and biomechanical. So 3D CAD designs plays more and more important role in this field. And therefore engineers and designers spend like quite a lot of time on CAD daily. So CAD search can provide an easy reuse of the previous similar CAD designs. This helps engineers and designers to save a lot of time and money by not creating the module from empty sketch every time. And also be able to search CAD files based on the geometry also helps to allow authentication of files. Like the engineers and manufacturers can verify the CAD design based on the pre-built CAD database. This helps to capture the copycat 3D designs or unauthorized CAD files. So we got inspired from the audio search algorithm by using spectrogram, which is a 3D graph in time, frequency, and amplitude. Therefore, the first step of our approach is to transfer the CAD file into the frequency domain representation, which is spectrogram. And then for each spectrogram, we generate a set of fingerprints to represent the CAD files. And we will introduce fingerprints in details on the later slides. And based on those fingerprints, we design a search function. The search function provides exact match and also can output a set of CAD files that contains similar geometry. We also create a database to support the search function and test the approach. So the first step of this approach is to convert the CAD file into a sound format. There are two commonly different formats, CAD formats are commonly used to represent the CAD files in the industry. One is step format and another one is STL format. Those two formats are slightly different in coding. So STL format supports binary representations, which can be used to generate the sound file directly. But step format does not support binary representation and only in ASIC representation. Therefore, if we have CAD files in step format, we need to convert it to text format first and then convert to binary representation. Once we have the binary format text file, we can use Python wave module to generate the sound in wave format. Here is an example of sound format we generate from this robotics arm. I can play a short time. It's a little bit like loud and annoying random noise. Yeah, so it's like a random noise, but it's successfully converted from the CAD module. And using the proposed approach, the same CAD module geometry can be recovered from that sound file. The conversion is fully reversible and lossless. First, we use the wave module library to read the audio file and generate a new text file with binary data. Then the binary text file converted to step file design, like a CAD design directly. We also test the work by converting the sound file back to the CAD file, and the CAD files can still be able to open in the CAD, 3D CAD software like SolidWorks, and the geometry keeps the same. So once we have the sound file, for each sound file, we apply fast Fourier transform to generate the 3D spectrogram from the CAD file. In Python, there is a library called SignPy signal spectrogram to do this job. The library function returns an array of sample frequency, array of sample time, and the spectrogram. Shown as the figure on the right bottom, the x-axis is represented as the time, and the y-axis is represent the frequency, and the color represent the amplitude. So once we have the spectrogram, each spectrogram represents a different CAD file. But if we store the entire spectrogram information into the database, it costs the time and costs the space. Therefore, we have to determine which part of the spectrogram can be used to represent the CAD file. So what we did is we treat the spectrogram as a graph, and then we try to find the peaks from the spectrogram. We store the coordinates of the amplitude peaks as a fingerprints, which we call ID stamps, to represent the CAD file. The reason is each CAD file has different size. Even the same size, like the same CAD file, can generate different size of spectrogram with different frame rate setting. Therefore, we cannot store the absolute value of the amplitude. Instead, we store the coordinates of the amplitude peaks, which is a list of pair of frequency and time indices. In this way, the sampling rate does not affect the ID stamps. A CAD file will have exactly the same ID stamps, even with different sampling rate. We use sliding window technique with maximum filter to find the peaks. The idea is to employ a sliding window as the input and replace each amplitude value with the local maximum amplitude within its neighborhood window. For example, the example provided here is we have a 5x5 spectrogram as the input image, and the slide window size is 3x3. So the maximum filter used 3x3 slide window to filter the local maximum value and returns a new multidimensional array. And then the algorithm compares the new multidimensional array with the original spectrogram to get the coordinates of the maximum amplitude. Those are the ID stamps. And the number of ID stamps major depends on the window size. So once we generate the ID stamps, we need to figure out how we store those ID stamps. So to store the ID stamps and support the search feature, we used MySQL connector Python to build a MySQL database. And most importantly, to successfully not only find the exact match, but also find the close matches. The algorithm does not store all the ID stamps along with its corresponding file name into the database as a single entry. Examples show us the right side, like the table here. The pairs of frequency and time indices are stored individually along with the file name into the database. So in the database, each file contains multiple entries of ID stamps. This approach gives the freedom to calculate the similarity index between the two candidates file. So for each search, we will calculate the similarity index. The similarity index captures the ratio of matching ID stamps with the total number of ID stamps. So which means similarity index evaluates the matching rate between two candidates files. And for each search, first the system takes the input Karri CAD file and generate a list of ID stamps. And for each ID stamps, it's run the search in the database and keep tracking the total number of ID stamps for each CAD file in the database. And also the system tracks the number of matched ID stamps for each CAD file with the Karri CAD file. And to determine whether the file is in the database is a match or not, here we like to introduce the function to calculate the similarity index. First, because the size of each CAD file is different, so the size of spectrogram is also different. Therefore, the absolute number of ID stamps associated with each CAD file may not be the same. So when we calculate the similarity index, there are two limitations. First case, when t larger d and d equal n, what does this mean? So t represents the number of ID stamps in the Karri input CAD, and d represents the ID stamps for each CAD file in the database. N is the number of matches between those two files. Let's give an example. Let's say if I have a file A contains 2000 ID stamps, which is shown in the blue color. And if the file B contains only 200 ID stamps, the maximum possible matches are only 200. If the equation for the similarity index use purely like simply n divided by d, the result will be saturated to 1, but it's not the truth. Since the input Karri files contain 2000 ID stamps, file A is not an exact match as file B. Similar issue happens with case 2 when the input file has a fewer ID stamps. Therefore, to cover those two corner cases, the similarity index formula computes the sum of the number of ID stamps from both files as the total number ID stamps. And then the number of matches just divide by the average of those two files to compute the similarity index. And the range of similarity index is from 0 to 1. 1 is represent the exact match, and 0 represent no match. Here is an example output shows on the right side. The system ranks all the files based on the similarity index and output. So to conclude, the new approach enables searching and retrieving CAD files based on the geometries and time frequency domain. The system outputs the exact match of geometries of various shapes and similar shapes as similar matches. With the experiment under more than 2000 files database, the converted sound are also fully reversible and lossless. Here I'd like to give an example run search to show how the search conduct. Are you able to see the screen? So here is the algorithm, and let's say if the input file name is 41 WAV, which is the 41 step file, and if I run a search, the algorithm first converts the input Karri ID stamps, and here shows the number of ID stamps for the input Karri Karri file, and then it runs all the database and give the search for each files. At the end, the output can show like 41 WAV has similarity index 1.0, which is exact match, and it also has the similarity match, the rest of similarity matches. So back to here, back to the PowerPoint. So for the future work, we still need to conduct more experiments based on a larger database to verify the deep connection between the meaning of geometry and the ID stamps. We also need to want to build a public website to support the public users to visit the search engine. To support this, we will move the local database to cloud. And also, we will design method to provide different input options for user to input the query files. Thank you.